Alright, everyone. Today we're going to explore the hydraulic and energy grid line. Alright, so this week we're supposed to finish these two parts, right? Hydraulic and simple part system. So, what do you know about hydraulic and energy grid line? Anyone would like to try? We'll give you 10 points. Okay. Anyone have any idea what is hydraulic? Hydraulic.
Does it support the force?
Pardon?
It is used to support force.
It is used to
support compression or tension force.
I cannot hear you because the sounds because of your background noise.
Can I try?
Okay, you can try.
Is the power produced by water?
Yes. Hydraulic.
When we brush a liquid.
Okay, basically hydraulic is related to the energy relation to the fluids, alright? So it is more on the pump. Okay, hydro. You can see hydro. It is a water. It is a fluid. This is the energy of the fluid. So sometimes we call a pump. Okay, coming from the pump. So energy grid line, on the other hand, is basically the kinetic energy. Right? I will explain later on. So hydraulic related to the pressure that push the fluid. So the pressure coming from the pump, and the energy grid line is the kinetic energy. Okay, the movement of the fluid, kinetic energy due to the potential energy. Okay, so I will explain on this part. So based on the energy equation that is written in the form where the term have dimension of length. So what's the energy equation? Okay, let me see. Okay, the energy equation you can see. Yeah. Alright, the energy equation you can see basically when we involve 2 points, so P1 over gamma plus V1 squared over 2G plus Z1 equal to P2 over gamma. This is basic, yeah. V2 squared over 2G plus elevation at point 2 plus maybe we have the mechanical device like work of the shaft over mg plus head loss. Okay, so here you try to rearrange, you will find out that this W work rate, you can be like the first left hand side, right, over m dot g is equal to V2 squared minus V1 squared over 2G plus P2 minus P1 over gamma plus Z2 minus Z1 plus heat loss. Okay, you can see all these we move to the right and the the work of the shaft, we move to the left. Okay, you can see that the term have dimensions of length. Alright, because previously we learned about dimensionless, where no unit at all. But you can see, do you think this is the homogeneous equation? Anyone? Do you think this is the homogeneous equation? Yes or no? No or yes?
Yes, doctor.
Yes. Why
Yes,
it
yes,
is,
doctor.
why it is homogeneous?
It has no dimensions.
Because
Because
all these term, okay,
The length.
has the same dimension, which is L,
Length.
length. Yeah. Right. So from here, for example, like velocity, you can see v, okay, v2 squared minus v1 squared over 2g. Okay, so velocity, what is the formula of velocity? Sorry, what is the unit? Meter
Per
second
second.
negative 1. And this is the power of 2. Divide with, we consider only the parameter only. Gravity is acceleration, meter second negative 2. So, meter squared as negative 2 over meter second negative 2. So, cancel, 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 cancel. You can see it is the unit of meter, which is the dimension of length. Alright.
Doctor,
Hmm.
for the first equation, why you didn't add the H turbine and H pump? And then you assume that there is no turbine and there is no pump, so you just cancel out
Okay, this is
from
just
the first
arrangement.
equation.
If the first equation, okay.
Yeah, the first one up. You assume that there is H loss, right?
Yes.
So
Okay.
why you didn't just assume that there is H turbine or pump, and then if it's not, then you just cancel out, but you write it there.
Okay. It's okay. You can cancel at the beginning. Basically the final, the complete equation, I believe you know, which is P1 over gamma plus V1 squared over 2G
Yes.
plus Z1 plus another one, Ama?
H pump
Heat pump. Okay, I want you to convert into W.
into
Into W, work of the pump.
S. Or you mean the full one?
The full one.
P over mistaken.
Over mg, okay, equal to P2 over
2
gamma
over gamma plus V2
2 squared
squared
over
over
2g
2G
plus
2,
work of the shaft. This is the turbine, okay, or
and the Z2 is
okay, this is the turbine,
yes,
okay,
turbine.
mg plus heat loss. Okay, basically this is the work. So because of this work from the pump, this work from the turbine combined to be like this. This is the single. Okay, so because the pump have the shaft, right? We have the shaft.
Yeah.
The turbine have the shaft. So we combine this together, we form only single one. Basically, you can write this one. It's okay. This is the second version. Okay, Ama?
Okay. Thank you.
Okay, welcome. So based on this, you can see you try to form the dimensionless parameter. You notice that it is the m meter, the function of length. Same goes to the pressure. You can see the pressure. Where is the pressure? P2 minus P1 over gamma. Okay, so what's the formula of pressure? Pressure is equal to force over area. Okay, gamma is, what is a gamma? Rho multiplied with the gravity. Okay, the force is equal to mass multiplied with acceleration. Okay, so The mass is kilogram. The acceleration is meter second -2 over area meter square over with rho, which is the density is mass over volume meter cubic multiplied with the gravitational acceleration, which is m as -2. So try to cancel out meter second -2, kilogram, this one become, and then we move to outside, become meter. So we notice it is in terms of length, right? So the velocity here, the terms of velocity basically we call the energy, okay, in terms of energy, all right? It is the unit of length. In terms of pressure, we call, sometimes we call a hydraulic, all right? It costs the hydraulic. The velocity term, it costs the energy terms, right? So the hydraulic and the energy grid line for piping system can hence be defined by, okay, you can see here, the term have the dimension of length. You can see we have length. We have length. This has led to the, okay, because of this, all this dimension is homogeneous, right, with the dimension of length. This term which have the length, this is the length, heat loss length, this is length, this is length, this is also length. Because of this length, all right, because of this length, this has led to the conventional use of hydraulic grid line, all right. The line we can reflect into line, and the energy grid line. So this is line, all right. So the hydraulic and the energy, remember hydraulic is the pressure term. The energy is the velocity term. For piping system can hence be defined by hydraulic grid line, we call as simply as HGL, located at distance P over gamma above the center of the pipe, all right. Where is the center of the pipe? This is the pipe center. Okay, I believe you know this is the pipe center. Above the pipe center with the length of P over gamma is this dotted line we call as the HGL, hydraulic grid line. Okay, this line primarily dominated by the hydraulic, dominated by the pressure, all right, by the pressure difference between two fluids, all right. So for the energy grid line, which is located at distance above the HGL. So where is the HGL? This is the dotted line is HGL. Above the HGL, with the distance of this value, B squared over 2G is the EGL, energy grid line. Where is the EGL? You can see here. Above the HGL is the EGL. Okay, this one, the full line here, right? So let's start to do a simple demonstration for this case. Okay, so we start from the left and finish to the right. Okay, so energy start from potential energy due to the difference in height. You can see we have the height. Okay, we have the height. Okay, this energy, all right, we have the potential energy at here, and at this point, when the fluid enter this line, okay, do you think where the energy come from this one, the move of the fluid, due to what? The water can enter due to what?
Friction.
Huh?
Friction.
Due to friction.
Due to pressure.
Pressure.
Due to the pressure, okay. Okay, you can see we have the punch, we have the like this. This is pressure. Okay, the pressure pushing the feed here. So because of that, the pressure enter push the feed entering the pipe inside here. Okay. Right. So the water coming from here, right? So you can see initially we have a certain amount of energy. Okay, when the water entering this section, the pressure drop. You can see why the pressure drop, slightly drop when entering this section. Why drop? Okay, let me call upon Muhammad Nursat Alam from section 1. Are you there? Nursat not coming.
Yes, doctor.
Okay, Nursat, why there is a slightly drop of pressure, hydraulic grid line when entering this pipe section?
Can I try, doctor?
Okay, you may try. So what's your name and section?
I'm section 1, Ibrahim. I'm Ibrahim.
Okay,
Right?
Ibrahim, can please
Yes.
try.
Because this point before bump.
Because of what?
Because this point before bump.
Bump? What do you mean by bump? B-U-M-B?
Yes, bump. Yes, before bump. So this is a drop pressure.
Okay, I think it is not accurate. Anyone would like to try?
Can I try?
Okay, please.
Is it because converted to kinetic energy?
Not really.
Sir,
Doctor,
may
can
I
I try?
Okay, please.
Because the pressure drop is actually works as a resistant mechanism for the flow when in tanks and piping systems.
No. Okay.
sir,
Have
may I
you
try?
okay, please.
Uh, because of the height of the water decrease and then the pressure drops.
Okay, I think no. Okay, do you come my last class?
Victor, can you repeat the question?
Okay, why there is a slightly drop of the what we call here the HGL, the hydraulic grid line, the energy coming from the hydraulic, the energy coming from the water slightly drop. Okay, Ronak, you want to try? Okay, you may try.
Is it because you want to increase the velocity?
I don't want to increase the velocity because you can see the velocity drop. Okay, Chin Rong Xiang.
Is it minor loss?
Okay, can you explain further? Minor loss?
Because
Sir.
the outlet there,
Okay, there.
parallel to the pump, there's an exit, so there's a minor loss.
Okay. Correct. Okay, your name Chin Rong Xiang from section?
Section 2.
Section 2. Okay, you got 10 points. Okay. Alright. When you look at my previous lecture, do you notice that we cover the minor losses? Remember the minor losses coming from the pipe geometry, the change of pipe geometry from smaller section to the bigger section, we have the loss. From the bigger section to the small section, we have the loss, the contraction of pipe. Alright, you can see K. K is the sudden expansion or sudden contraction. So because of the sudden change of geometry, we have the minor losses. Because of minor losses, this will contribute to the loss in the hydraulic grade line or loss in the energy of the fluids. You can see here, the last class we did the example. From here you can see the entrance. This is the K entrance, the coefficients of entrance. We have loss. How much? 0.5. And then we have the elbow loss, which is 0.64. Do you still remember? Right. So we have the minor losses due to the sudden change of geometry. Okay. Now you understand, yeah? So this is the drop due to the minor loss, sudden change of geometry. Now focus on HGL, hydraulic, due to the pressure. So slightly drop, a little bit drop, not much, slightly drop, all right? And then continue to drop, okay? Continue to drop linearly, okay? Until it reach the pump. So what's the function of pump? Anyone? The function of pump.
Increase energy.
And not accurate. Increase what?
Velocity.
Not accurate. The pump. Can you try to Google what is the function of pump? Anyone? Please Google. When you go for the job interview, for the Rainhill company, okay, they might ask you what's the function
Increase
of pump?
increase pressure.
Yes, the function of pump to increase the pressure. So that is why the pressure from this point increase to this point. That is a function of pump. Okay. So at this, okay, and then after that, going out of the pump, drop of the pressure due to the why? Due to why there is a slightly drop.
Minor losses, doctor.
Minor or major?
No, major because they are linked.
Major, all right. The friction along the pipe is the major. The bending of the pipe, the geometry change is the minor, right? So this is the major losses. This is the major losses. This is the minor losses. Okay, and then you can see we have the valve. So what's the function of valve? So what's the function of valve?
To increase the pressure.
Increase the pressure.
And the velocity.
Okay, the function of valve.
Decrease the pressure and increase the speed.
Basically, yes, the function of valve to regulate the pressure, or that means to control the pressure. For this case, it is used to decrease the pressure, right? Because we have the valve to control, to give the obstacle. This is like a resistance, okay? And then there is a slightly drop of pressure. And then the pressure reduced linearly due to the major losses, friction along the pipe. And then you can see there is a slightly change of geometry. It is a expansion, suddenly expansion. Okay. And then the pressure increase a little bit only. And then drop linearly due to the friction along this section. And then this is the sudden contraction. Okay, smaller geometry, so it is reduce the pressure. And this one, it dropped significantly linearly due to the major losses, the friction along the pipe. Until this section, the energy at this point same elevation as the energy at the water surface. Okay, that's what we call the the atmospheric pressure. Okay. All right. Because of the hydraulic, all right, the pressure of the fluid, it will cause the movement of the water. When you push the fluid, it will cause the motion of the fluid. So start from here. Okay, the velocity reduce. Okay, the kinetic energy reduce along the pipe. All right, and then due to the major losses, all right, because of the friction, it will try to hinder the motion from moving. It try to push the motion. All right. So and then we have the pump. The pump will increase the pressure as well as the velocity. Due to the pressure, increase the velocity. So the velocity increase and decrease due to the major losses, and we have the valve to regulate the fluid drop slightly. Okay, you can see the difference here is the HL, heat loss, from the valve only. Okay, not heat loss from everything. And then drop due to the major losses and drop due to the sudden expansion of this geometry, and drop. All right, and finally at this point. Okay, so this is the HL. So that is why because of this energy, you can see here the water can flow. Okay, when the energy, okay, without this kind of energy, definitely there won't be any kind of movement of the liquid or water. Okay, this one I already explained. Okay, for example, when we have the turbine, the function of turbine to extract, to get the energy from the fluid, so it will reduce the hydraulic grid line. When we have the pump, it will increase the energy, and so on. Okay, let's start with this kind of example. Okay, the water at 20 degrees Celsius. Okay, when you look at this kind of question, first give the temperature. So what can you relate the temperature with one parameter?
Viscosity.
Yes, perfect. Different temperature will give different viscosity. So indirectly, the question won't give you the viscosity, the kinematic viscosity. It will give you the temperature. This is indirect question. Give you temperature. So you need to refer to the table to find the viscosity. Flow between two reservoirs. We have this one and this two reservoir. With the datum here, elevation 0. At the rate of, this is the flow rate. Q. So what can you relate the Q with one parameter? They give you the Q. Huh? Yes. They give you the flow rate so that you can find the velocity. You can see it is indirect question from the AV as shown in the figure here. Sketch the hydraulic grid line and EGL, and what's the minimum diameter allowed to avoid the occurrence of cavitation. Okay, first of all, let me explain a little bit about cavitation. The cavitation is where the local pressure less than the vapor pressure. It will cause the cavitation in simple word. Okay, cavitation. Cavitation is like a bubble. When you try to search, okay, let me explain a little bit. Okay, cavitation. Okay, this is the cause. You can see. This is the blade. Okay, sorry, this is the turbine, I think. The turbine blade. All right. You can see here, this is damage. The damage due to the cavitation. All right. So many engineering company try to avoid cavitation by adjusting the fluid flow. So this cavitation is actually like the bubble, like a bomb, like a small bomb, the small, very, very small air bubble inside the water. It like explode, pop, pop, pop. And then it, with so many of air bubble, it form the cavity. So this air bubble will explode this area, okay, this wall. This is due to the cavitation. So to cause the cavitation, the local pressure, you must be wondering what is a local pressure, is less than the vapor pressure. Okay, for example, this is the water. All right, and this is the turbine propeller. Right, try to rotate here. So we have the vapor pressure. Okay, in every liquid, they have their own vapor pressure. When this turbine try to move at certain speed, okay, for example, this is turbine blade. This is inside the water. Okay, this turbine try to move at high velocity. What do you think of the pressure? High velocity will give you high or low pressure?
Low pressure.
Okay, low pressure based on the Bernoulli. Okay, Bernoulli or based on the Bernoulli equation, correct? Okay, so this pressure at this point, maybe this point, the local point, the pressure is very low compared to the surrounding vapor pressure. So it will cause, by nature, the air bubble, the small tiny air bubble will explode and damage this propeller. That is why you can see in the picture there. Now you understand, yeah? Because of the local pressure less than vapor pressure. Okay, so now to avoid the occurrence of cavitation. So in order to do this, first we draw the EGL and HGL. So this has been drawn. The first start at this from the left to the right. Alright. So from here, the water coming here, due to the sudden contraction, we have the significant slightly drop of the pressure. Okay, as well as the kinetic energy, EGL. And then continuously drop due to the friction along the pipe. And then we have sudden contraction again. We have slightly drop. This drop is much drop. You can see. Okay. And then flow to this pipe, drop linearly, and we have the sudden expansion of the increase a little bit and drop linearly due to the friction along the pipe. Basically, the EGL energy grade line just follow parallel to this section. But for this one, okay, it's slightly drop. Okay, the geometry will increase the velocity. That is okay. But due to the friction along the pipe, drop and then drop a little bit until this section. Okay, so from here, okay, after we have understand the energy grid line, okay, please make sure you know how to draw. Hydraulic is a dotted line and label it. Please make sure label, and then you label like this. Okay, make like this arrow and then this arrow. Okay, don't simply make like this. Make an arrow. Okay, and then please make like this. The difference between the EGL and HGL is V squared over 2G. And from here, okay, you can explain from the center here to here is P over gamma. Please explain like that when you encounter for your exam or for your test. Okay, this is not the hint, just give you a precaution. Okay, so first, since we know the Q, let's find out this V. Alright, so let's find out the, okay, let's say this is section A and this is section B. You can see label section A and section B. We need to make the separate section. Why? Because the pipe have different diameter. So let's say this is section A and this is section B. Okay, so at section A, right, we have diameter 0.2 meter. Alright, 0.2 meter refer to 1, 2, 3, 0.2 meter diameter. So Q equal to A V, velocity at point A. Let's say this is velocity at point A. So in order to get velocity A, point A, section A equal to Q over A. So Q is given 0.06 meter cubic per second over area. Area of this is, alright, cross-sectional area is pi d squared, okay, 0.2 over 2 squared, okay, pi r squared. So you try to solve, you will find the answer is 1.91 meter per second. This is the velocity we already found. Okay, based on this velocity, what can you find next? Because we have the drop of the energy due to the major losses. That means we need to refer to the, anyone? What kind of chart? What kind of graph that we need to refer? What we call?
Moody diagram.
Moody diagram.
Yes, we need to refer to Moody diagram. Because from the Moody diagram, we can find the major losses, which is F. So in order to get F, what we need to find next? We need to find the
Reynolds number.
Reynolds number. Alright, because in the Moody diagram, this is Moody diagram. This is F. This is relative, what we call relative roughness, and this is Reynolds number. So in order to get this parameter, friction, we need to find RE and ED. So Reynolds number is, okay, velocity diameter over nu. This is nu is kinematic viscosity. So velocity is here, 1.91 multiply with diameter of the pipe 0.2 over with nu. How to get this nu?
From the table.
From the table. When you look at the table, what parameter you need to know?
This pressure.
You need to what? In order to get the nu. Okay. Property of the water. Where is the property of the water? Yes. Okay. This viscosity or this viscosity? Which one correct? Left or right?
Right.
Kinematic.
Yes, kinematic. Please don't confuse. Yeah, this is kinematic viscosity. VD over nu. For this is we call a dynamic or absolute viscosity. This is rho VD over mu. This is mu. This is nu. Nu. Okay. So based on the temperature given here, 20 degrees Celsius. So 20 degrees Celsius temperature will give you the nu. which is 1.007. The power of multiply with 10, the power of negative 6. Okay, try to substitute this one. Okay, you will get the answer here. This one at 20 degrees Celsius. You'll find the answer to be 3.8. The power of 5. So this is considered turbulent or laminar. And what the critical number for the for the laminar?
Turbulent because it's more than 2000.
Yes, perfect. Abdul Rahman. So your section and your name, you got 10 points. Abdul Rahman. Section 2. Abdul Rahman.
Yes.
Which one? Start with A. This one?
Yes.
Okay, 10 points for you. Thank you. Okay. So once you get the Reynolds number, next you need to find the relative roughness, E over D. So is it given the types of material? Okay. Let's find out. Okay, water at 20 flow between two reservoirs shown in figure. Sketch the what is the minimum allowed to over accurate can be. Let's find out. This one, this one, this one. Okay, let me find out first. Okay. Lecture note 9. Wait, yeah. Okay. Okay, this is the Moody diagram. Okay. Okay, I think the question using... Okay, just add information. The question use the cast iron. Okay, 0.26. Maybe, sorry, this question is not given. Okay, please add using the cast iron. So when we look at the material to be the cast iron, this one, okay, okay, because sometimes the question will ask us to predict, okay, the suitable material is the cast iron because this is for the normal usage, right? Because need to supply between two reservoir. The cast iron is quite cheap and long lasting. Okay. So they use the cast iron 0.26. So the E is 0.26 mm. 0.26 mm over diameter should be mm as well. This is 200. 200 mm. Make sure the unit should be consistent. So you'll find out is 0.0013. Okay, based on the Reynolds number and the relative roughness, directly look at the Moody diagram. So 3.8 the power of 5. Okay, so 3.8 the power of 5. So this is the power of 5, 3.8. So this is 1, this is 2, this is 3, this is 4. This is 3.5. This is around here. Okay, so using a ruler, draw this straight line. Okay, and then the relative roughness to be 0.0013. Where is the 0.0013? 2. This is 1. This is 2. Okay. This is the middle is 0.0015. So around here. Alright. So this is maybe around here. Just follow this line. Okay. It is not straight, yeah. It is curved a little bit. Okay. Sorry. Supposing this is the curve. Yes. So this point is the intersection. From here, okay, straight away go to this line. Okay. So read from here 0.02. This is 0.025 in the middle. Okay, 0.0 from here. Okay, it is around 0.1, 2, 3, 4, 5. So 0.022. Okay, it is correct. Okay, based on the solution, it is 0.022. So the friction here is 0.0. Okay, is 0.022 based on Moody diagram. Alright. So this is only this section. How about the section B? So again, we need to do the section B. Section B. Alright. So in order to get VB, I make it fast here. So V equal to Q over area. So Q is the same. Remember that the flow rate is the same, still the same. Right? The flow rate will never change across the pipe. 0.06 over with area pi diameter. The diameter is what the question asks you to find. Alright, propose the minimum diameter dB. So just leave it the answer. Pi d is squared over 4. That's it. And then try to solve. You'll find the answer is okay, 0.0764 over with dB. This is the relationship. VB with VB with dB. And the Renault number. Renault number is VD over nu. So V is here. Just substitute the value 0.06764 over dB. Diameter is diameter. Okay, the diameter of B over with nu, which is 1.007. I believe you understand previously. 10 to the power of -6, and then you will find out the answers to be okay 76400 over dB. Okay. So from here, find the E relative roughness. E over D, which is 0.26 millimeter. Convert to meter because we're going to substitute over dB. Okay. So once you substitute the parameter, please put the full SI unit. 0.026. Okay. So, the minimum possible diameter is established by recognizing that the water vapor pressure at 20 degrees Celsius is the minimum allowable pressure. Okay, so in order to cause the cavitation, okay, we need to assume the minimum pressure is equal to the vapor pressure at this point. Okay. Okay. So the vapor pressure at this point, okay, the minimum possible diameter is established by recognizing that the water vapor pressure, okay, the minimum pressure P minimum should be equal to the P vapor pressure at 20 degrees Celsius. Okay, at 20 degrees Celsius, the absolute vapor pressure, okay, when you look at the table, the value to be 2450 Pascal. This is absolute, okay. When you deal with the cavitation, please use the absolute one, all right. You cannot use the gauge pressure. Okay, so this is the absolute one to find that relation to the cavity. So, all right. So you can see at this point number 1 and point number 2. Okay, or you can see along the point from point at reservoir 1 and reservoir 2, which one consider having very low pressure line, which section, which point? From the reservoir 1 to the reservoir 2, what do you think, at which point the pressure is very minimum? Anyone? Aina? Which one do you think very minimum?
I guess number 2.
Yes, number 2, because you can see this line. This line is a line of pressure. There is no more line that is below this point. That is why this point number 2 is minimum pressure. Alright, this minimum pressure should be equal to the P vapor pressure. If this vapor pressure less than this value, for example, if this P minimum less than vapor pressure, what happened? So what happened? Does the cavity will happen or otherwise? If the pressure here is less than vapor pressure at this point, what do you think? The cavity happen or not happen?
It will happen.
Yes, cavity will happen. So now we assume that P minimum is equal. Once we get that value, should be more than our calculated value to avoid. So now assume that P minimum is equal to vapor pressure as our baseline, because the question asks to avoid the occurrence of a cavitation. So in order to avoid, just assume it is equal first. Right? So let's use the energy equation at point 1 and point 2. Okay, our energy equation at point 1 and point 2, V1 squared over 2G plus P1 over gamma plus Z1 equal to V. Okay. Once you consider this point 1 and 2, use at point 2. V2 over 2G plus P2 over gamma plus Z1 plus head loss. Okay. So V1 Do we have velocity at point 1? No, because the velocity is very, very small based on the continuity equation. The pressure is, okay, so here we can cancel out. The velocity is 0. Z1, sorry, Z1 is not 0. Z2 here is 0. Why Z2 is 0? Because you can see here, okay, you can see at this point, not this point, yeah, actually this region, yeah, it is datum line. This is the energy grade, this is the hydraulic grade line, this point, it is 0. So we can cancel Z2. Alright, so from here, try to rearrange. So P1 over gamma plus Z1 equal to velocity at point 2. Velocity at point 2 relate to the VB, the velocity coming from B. So VB squared over 2G, okay, plus P at point 2 over gamma plus heat loss. We know that the heat loss is coming from the major plus minor losses, which is major is FL over D, B squared over 2G, and minor summation of K, B squared over 2G. So try to put all the value of major and minor losses. Start with the entrance, K entrance, VA over 2G plus K contraction, V B squared over 2G. You can see A coming from the entrance, okay, this entrance. And the contraction is related to VB. That's why VB. And then you have the major loss, F coming from the pipe A, LA over DA, VA squared over 2G plus friction coming from the B, which is LB over DB, okay, VB squared over 2G. Alright, after this, try to okay, rearrange the equation lah. I try to rearrange for you. P1 over gamma plus Z1 equal to, okay, VB. We start with VB. We try to factorize and we group together VB, VB, and this VB. So VB squared over 2G bracket. This one refer to 1. And then this one refer to K plus K contraction relate to B plus K contraction due to B, yeah. And then we have this one more plus F L B, this is B over DB, close bracket. And then continue with P2 over gamma. Okay, and plus A, this is A, so VA squared over 2G bracket, this is K entrance, start with K entrance. This is A and then this is A plus F A L A over DA, close bracket. Alright, so you try to substitute all the value. Okay, all the value. Okay, this is almost complete. I try to substitute P. This is the P atmosphere because this is using the absolute, yeah. So this is not 0, absolute 101,000 over 9810 plus Z1 is 20 because the elevation here from the datum, you can see from the datum to here is 20 meter equal to VB. VB is found already from this relationship 0.0, okay, 0.0764 over dB squared over width. Okay, you can see basically this is squared, yeah, because we have the square here. All right, to gravity 9.81. Okay, and then all right, you need to plus this one. Okay, this one 1 plus K contraction. Okay, the K contraction you look at from the table. Okay, Control F, enter. Okay.
Doctor.
Yes.
I have a class now. Because it's up lunchtime. So.
Okay. It's okay. I will continue next about this. Okay. I will continue later on. Okay. So until this section. Okay. So I hope that you understand for this section. I end my section with Assalamualaikum.
Doctor, I have a question.
Yes.
Doctor, it's regarding the test. So the syllabus is till week 11, but we have the similitude and the Buckingham pi theorem is in week 12, but the dimension analysis falls in week 11. But we cannot. I mean, the questions of dimension analysis is with similitude. It's together. It doesn't come alone. And
okay.
And our other lecturer, means our friends in other section, they said that it's also not in part of the test, the similitude, the dimension analysis. So can you please confirm on that?
Okay. Yes, it is confirmed. So lucky for you.
All right, thank you, doctor. Because without similitude, we cannot use dimension analysis. I mean, not much benefits.
Yeah, I understand.
Yeah, thank you.
I will send the email. Okay, today. For those try to crack the password, you cannot crack because the password is very long. I will give you the protected question after this, question 1 and 2 for different set. Yeah, you will get different set 1 or set 2. Okay. So anything else? So for those if your official email is not working, please let me know, because after this I'm going to generate sending you all the email. Okay, I hope you can look at your official email, graduateutm.my.
Excuse me, doctor. So
yes.
So for the test we have only 3 questions, right?
Two
questions.
Okay.
Because question 1 and question 2 combined, 10 mark. Question 3, 10 mark. So 2 questions only. 1 question each. You need to complete 45 minutes.
So how much is the percentage?
The percentage is 20.
So doctor, we solve each question and submit, or like last time we submit all together?
No. You solve first, you submit. Solve and submit.
Okay.
So the test is until deflectors and propellers, doctor?
Pardon?
The test is until deflectors and propellers?
Propeller?
Yeah.
Might be. But I can confirm lah, the simulated and dimensionless not included.
So doctor, up to which chapter? So I'm just confused. Bike theorem, is it include or not?
No. Dimensionless is not included. Dimensionless include the Buckingham pi theorem.
So only we have the conservation of energy and momentum and mass, and Buckingham theorem.
Yes.
Buckingham theorem is not there.
Buckingham theorem not include. You will include the Renault transport theorem RTT. Please. Okay.
Okay.
Doctor,
So
can you share with us previous test?
the previous test.
Just like example, because we don't have it.
Okay. I will share in the e-learning. You want the you want the question or you want the answer script?
Questions and answers, please.
Question and answers.
Okay. Okay. After this, I try to search again and then upload. Okay. So after this, look at your email address. Okay. I end my. Anyone?
The Telegram group is it? We should join it in case of emergency, or we should we should join it now.
You should join in case you yourself not receive the email. So I will immediately give you the password through the Telegram. So that is why my precaution, I'm worried that you might not receive the email or the email spam, going to the spam, and then you panic, and then just join the Telegram group, and then I will share from there. That is the emergency case.
Alright,
Okay.
got it.
Okay, I think that's all for today. Good luck for tomorrow at 9 o'clock. Yeah, please stand by at 8:40 p.m. because I'm going to brief to you the exam instruction.
Doctor, can you show the QR code again? Sorry.
Okay. Okay,
thank
anyone?
You,
okay, thank you everyone. Okay, goodbye.
Doctor.
Okay.
I didn't scan it.
Okay. Okay.
All right, thank you, Doctor.
Okay.